All right. So in this unit, there are different types of acid-base problems. And sometimes it feels for people like there's an infinite number of different types of acid-base problems. But in fact, there are really only 5. And so one of the things I strongly recommend in this unit in working problems is figuring out which type of problem it is. And that will help you a lot in solving it. So you can either have a weak acid in water, a weak base in water. And sometimes you can be fooled to say, oh, it's a salt and water problem. But a salt and water problem actually breaks down to a weak acid and water problem and a weak base and water problem. So it's really not a different kind of problem. And we'll see that in a few minutes. Then you can have a strong acid in water and a strong base in water. And then you can have, my good friend, the buffer type of problem. So those are the type of problems. And being able to recognize them is key to doing well in this unit. So let's look at work a problem in the first type of a weak acid in water problem. All right, so what's a weak acid? Well, vitamin C is a weak acid. And so sometimes when you're taking your vitamins, you get a bad taste in your mouth. And if you did take a vitamin C tablet here, which is 500 milligrams in this vitamin C tablet, and dissolved it in water. This is not scientifically measured, but dissolved it in water. So you were, say, taking your vitamin with a lot of water, and it was starting to dissolve and being pretty unpleasant. Then we could calculate at equilibrium what kind of pH we would have in that mixture. Now, these vitamins, this Nature's Bounty, they do a really good job of isolating the vitamin, so it is pretty much impossible for it to dissolve. So they have a nice coating around it that's highly protective, at least at normal water pHs, so it doesn't really dissolve. And one year I thought I would do the actual experiment. We could talk about significant figures, but I could not get the tablet to dissolve. I heated it, I stirred it, I did everything at neutral pH. At room temperature. I wanted to do it at room temperature. It just didn't work. Even at high temperature, it didn't work. So if you buy Nature's Bounty, it will not dissolve in the water that you're taking. So just for that little bit of information. But if you had, say, an inferior brand of vitamin C that that didn't have a nice coating around it, then you could do this experiment. So let's take a look at that. So the first thing that we have to do is calculate the molarity of the acid that we've added. So here you just have to make sure that your units are going to be correct. So we have grams. We're converting it with a molecular weight to moles. And then we have the number of moles in the amount of water. And we can calculate the molarity of that solution. And one of the mistakes that people often make in doing these problems, they forget to do all of the conversions that are necessary. Sometimes they stop at moles, and you're talking about concentrations here. So don't forget about your friend, the volume. All right, so then you can write an equation, and I highly recommend that people do this on the test because it helps them figure out what type of problem it is and avoids people making silly mistakes. So if we're talking about an acid in water, you should make sure that your equation reflects an acid in water. If you have hydroxide ion on the other side, something is very wrong that's going on. An acid in water is going to be giving hydronium ion concentrations and a conjugate base. So then we can set up an equilibrium table here. We calculated the initial molarity. And in the beginning, there's nothing over on this side. So we've just added our weak acid to water. And so then the change, there's going to be some amount of this that ionizes, minus X, some amount of this that's formed, and some amount of the conjugate that's formed. So we have 0.0284 minus X plus X plus X. Now we're talking about a weak acid in water. So what term am I going to want to use next? Ka. So I'm going to want to use Ka next. Ka value is here, 8.0 times 10 to the minus 5. We have products over our reactant here. And we have x squared over 0.0284 minus x. Now you can make an assumption when you're working on these problems and check it later. So you can make the assumption that x is really kind of small compared to this 0.084, and you can just drop this x out of the term here. And then check later and see if that worked or not. So that makes the math easier, and so now we can just solve for x, and x comes out to be 0.00151. They're really two significant figures, but we're going to carry an extra one for the moment. So they're just two figures right here, two significant figures here. Now we can check and see if x was really small, if that assumption worked right. So is 0.0284 minus 0.00151 really the same as 0.0248? And we let you make the assumption that it is. We say it's OK if it's less than 5% of the value. So in this case, it's actually not. It's 5.3. So that violates our policy. So it's more than 5%. So then you have to use the quadratic equation to solve the problem. I just want to note that this term, this percentage, can be called sometimes percent ionized or percent deprotonated, so that you're not thinking that's some kind of bizarre term if you see that. And if you use the quadratic equation, you get an answer of 0.00147. Again, that's really two significant figures. So it's not a whole lot different, actually, than the number you got making the approximation. So once you know what x is the hydronium ion concentration in this problem. And so we can plug that in. pH is minus log of this. So that's 2.83. And so we had really two significant figures here. And so we are going to have two significant figures after the decimal point here. And if you haven't reviewed your sig fig rules and need more help, if that seems wrong, then you should definitely review it before the next test.